Alright, so I was asked to work some problems. Let's start with Chapter 20, Problem 21. If I can get this machine to quit doing goofy things. Okay, so question 21, Problem 21 says that we have a magnetic field, and the magnetic field is going into the page, as indicated by the X's. And we have a proton moving into that magnetic field, and it has a speed of 2.2 times 10 to the 6 meters per second. And we know that it has a charge because it's a proton, and the distance of separation between the two plates is 0.18 meters. And as the drawing shows, a magnetic field exists between the plates and is perpendicular to the velocity of the proton. What must be the magnitude of the field so that the proton just misses colliding with the opposite plate? So we're looking for the size of B. So I said, well, I know that if it gets in that magnetic field, it's going to experience a centrifugal force that's created by the magnetic field acting on the proton. So mv squared over r is equal to bqv. So that's going to cancel, and one of those will cancel. So now I have momentum mv is equal to bqr. But I want to solve for b, so b is going to be mv over qr. So the mass of the proton is 1.67 times 10 to the negative 27 kilograms. The velocity of the proton was given to me as 2.2 times 10 to the 6 meters per second. The charge on a proton is 1.6 times 10 to the negative 19th coulombs. Negative 19th, sorry. And I want the radius of the circle to be, I want it to move just like that, or just like that. So I want the radius to be no more than 0.18 meters. So if I plug and chug, I get B to be 0.128 Tesla. Now, while we're here, let's take our right hand and figure out what the motion is going to be. So I want my palm to be the field. I want my thumb to be I want my palm to be the force. I want my thumb to be the velocity. And I want the, my fingers, extended fingers, to be the field. So it's going to get shoved. If I did my right hand right, and my right hand roll correctly, it's going to get shoved up something like that. So that's what's going on with number 21. Number 35 was the next one I was asked to work. And number 35 says, two conducting rails in the drawing are tilted upwards so that they each make an angle of 30 degrees with respect to the ground. The vertical magnetic field has a magnitude of 0.05 Tesla. The 0.2 kilogram aluminum rod that is 1.6 meters long slides down the ramp without friction, constant velocity. What current flows through the bar? Well, I know it has a bar, and it has a current because it's moving through a magnetic field and the charges are moving with it. So I need to do some artwork, so I'm going to pause for a minute and then come back. Alright, so here's my inclined plane. Here is my bar of aluminum. I'm going to use that as my free body diagram. I know gravity is pulling straight down, mg. I know that there's got to be a force normal pushing up. I know that the B field, I can draw it very well. It's something like that, or the force of the magnetic field, I should have said. And so it's got a component that's parallel to the ramp and perpendicular to the ramp. So I'm going to call this my force of magnetic field strength X and my force of magnetic field strength Y. I know that this has a weight component, mg cosine theta, that's equal to my force normal, and that this part of the weight is balancing that right there. I'm going to call this mg sine theta. And is there anything else I know? This angle right here would also be a theta. And you can go through the geometry to prove that. Alright. So this is FB cosine theta. And you probably need to pause this and stare at that and make sure that you can make sense of it and get it drawn on your paper. So if the net F is equal to MA, my only motion is occurring along the x-axis. So I have mg sine theta down the ramp minus FB cosine theta up the ramp is equal to the mass of the aluminum rod times the acceleration of the aluminum rod. It has no acceleration, so this whole side is going to go to 0. So mg sine theta is going to equal FB cosine theta. So I can say that mg sine theta, okay, the magnetic force is going to be BIL cosine theta. And they're asking me to solve for the current, so let's see what I know. I know that this is 1.96 newtons, because I think they told me it was a 0.2 kilogram mass for the aluminum rod. Let's make sure I'm telling you the truth there. Yes. So that's 1.96 newtons. There's my mg. This is a sine of 30. The strength of the magnetic field was given to me to be 0.05 Tesla. I'm looking for the current. The length of the rod was 1.6 meters, and this is the cosine of 30. So when I solved for I got I to be 14.14 amps, substantial current. All right, the next one I was asked to work was, hang on, let me check. Okay, so I'm looking at number 59 in chapter 21, and it says that we have 3 wires. We're seeing the ends of them, wire 1, 2, and 3. The current is going into the page for wire 1, into the page for wire 2, and then they're going to ask us something about wire 3. All right, so let's see what it says. All 3 currents are equal. No, I'm sorry. All the currents 1 and 2 are equal. So I1 is equal to I2, which we can just call plain old I. And they're directed into the plane of the page. What is the direction of wire 3, current in wire 3, and what is the ratio of wire 3 to wire I, such that the net magnetic field at the empty corner is 0. So over here, we want B to be 0. Okay. So I said, all right, well, let me see. If I'm doing that, then up here in this upper right corner, I know that I have a magnetic field surrounding this one, so I put my thumb into the plane of the page and my field is in that direction. I put my thumb in the plane of the page and my field is in that direction. And I don't know what to do over here, but I can look at this and say, well, let's see. At this point here, I have a field because of wire 1 that's pushing down, or pointed in that direction. I should say not pushing. That's not a good way to talk. So this one, at that point of the corner, is headed that way. And these should be the same size, since they're the same distance in the same field, same current. So there's B1 and B2. So the sum of those is going to be this right here. So that's the net B because of wires 1 and 2. So wire 3 has to create a field that opposes it, so these two cancel each other out. Hopefully that makes sense. 0. I want them to cancel out because I want the net field here to be 0. All right. So I said, well, let me see what I can do. Well, I know that B1, field 1, is going to equal field 2, and it's going to be equal to mu naught I over 2 pi r. And in this case, my r is going to be the length of each side of the square, which I'm going to call side S. So there's B1 and B2. And I know that B3 is going to be mu naught I over 2 pi. And I'm looking at this distance right here from my r. Well, that's the square root of 2 times S, because it's just the hypotenuse, diagonal of that square. So that's going to be radical 2 times S. And I know that B1 squared plus B2 squared is equal to B3 squared. Basically, I have Pythagoreans here. So if that's true, then I can say that 2 times B1 squared, which is mu naught I over 2 pi S squared, is equal to B3 squared. So B3 we said would be mu naught I over 2 pi square root of 2 S all squared. Alright, so let's just do the algebra. This will be mu naught squared I squared. We'll call that I1, or just I, over 2 squared is 4 pi squared S squared. That's equal mu naught I, mu naught squared I3 squared over 4 pi squared. Square root of 2 squared is just 2 S squared. So 4 pi squared will go. That'll go. And then I know that I have an S squared here and an S squared there. So it looks like to me I have 2 I1 squared equals I3 squared over 2, or 4I1 squared equals I3 squared. So if they wanted the ratio of I3 to I1, so then I have 4 over 1 equals I3 squared over I1 squared. Take the square root of both sides, so 2 over 1 is equal to I3 over I1, or I2, or just plain old I, however you want to address it. So there's my ratio. Right. So I'm going to stop there and go on next recording and do chapter 20.